Welcome to another episode of Earth is Our Home with host Dr. Thomas Blaine. Dr. Thomas Blaine is an associate professor with the Ohio State University Extension Program, and today he's going to be talking about ocean currents and gyres. So stay tuned. Welcome back to another episode of Earth is Our Home with host Dr. Thomas Blaine. Dr. Thomas Blaine is an associate professor with the Ohio State University Extension Program. And today we're going to be talking about ocean currents and gyres. Tom, it's always a pleasure talking with you.
Well, it's always a pleasure for me to be on here, Patrick. I enjoy doing Earth is Our Home. I want to thank you for being my co-host. And thanks Sarah Swanson for her assistance with our video series. It's a great opportunity to address the public on these topics centered around global climate change and global warming.
I agree with you. I understand about ocean currents, but what is gyres?
So the ocean currents are not just random phenomena. The ocean currents, the major ocean currents in the world, form gigantic circles. The ocean currents in the northern hemisphere, as we're going to see when I load up my slideshow, we're going to go through the ocean currents. And they form a giant circle that flows clockwise in oceans in the northern hemisphere, counterclockwise in the southern hemisphere. And so when you get that loop, like in the North Atlantic, for example, you get the loop, that loop is a gyre. It's called a gyre. As you recall, Earth is Our Home. That's the name of the overall series. Here we are in June. We began back in the spring and we're now proceeding to the summer. This is the 8th video I've done in this series, and we focused on Earth's climate, different aspects of Earth's climate throughout these 8. We did Earth's climate history for a few, then we went into the climate engine, and today we're going to focus on ocean currents and gyres because we're doing different aspects of how Earth's climate works. And you can't understand the climate without understanding the ocean currents. We've already seen, even from the very beginning, the very first lesson I gave, episode 1, you might want to go back and look at that. We found that Earth, during most of its history, has been a lot warmer than it is today. So when you hear people say, what's the big deal about global warming? Earth's been much hotter than it is today. Well, it's been 18 degrees warmer throughout much of its history. We're talking about tropical type climates in the Dakotas or in Ohio. You know, the kind of climate you got in Cuba or Florida in a place like Ohio. And the reason for that, the reason for the changes along that line are ocean currents. Normally speaking, you have currents that carry warm equatorial water up over the poles, unimpeded. They can't cool at the poles because of warm equatorial water passing by there. It can't cool anywhere, and we have a hothouse. Right now, as you're probably aware, both poles are cut off from tropical waters. The North Pole, you've got an ocean, the Arctic Ocean, but warm equatorial waters from the Atlantic, the Pacific, the Indian Ocean, they can't get near it because of land masses. These currents would bring warm water if they could, but they can't get there because of North America, Eurasia, Greenland in the north, and because of the continent of Antarctica in the south. Warm equatorial waters can't get near the pole. And so the poles can't get that moderating effect. And since the sun's shining angle is so severe at the poles, the sun can't really heat the poles or the polar areas. So think of the poles as Earth's air conditioners, because that's what they are. The reason we have a cold Earth right now is because of Earth's air conditioners, the poles, because warm ocean currents can't get anywhere near them. All right. Now, we've had this configuration for, it didn't happen overnight. Continental drift occurs very slowly. The continents move into their position very slowly. But think about this as millions of years, 10 million roughly on a scale of 10 million years ago. If you went back 70 million years ago, there was warm ocean water going unimpeded over the North Pole. So we couldn't have a cold climate. So Tyrannosaurus Rex lived in a tropical type climate in states like Montana, okay, where the climate was like Florida or Cuba. It's these configurations of continents, the effects on ocean currents that have an enormous impact. So I want to talk today about these ocean currents, how they currently work. That is, in the current alignment of continents, how are these currents working? But first, I want to go over the hothouse with you. If you look way out to the right, 0 years ago, we are about 12, 13, 14 degrees centigrade. It's in the 50s Fahrenheit, the upper 50s Fahrenheit, I believe, if you do the conversion. But if you look, we fluctuated between a hothouse, 22 degrees, that's 10 degrees Celsius warmer, that's 18 Fahrenheit, 18 degrees Fahrenheit warmer. Typically, the Earth kind of bounces back and forth between a hot house and a cool house. And that's because of the configuration of continents with continental drift. Whenever you see that temperature up at 22, 18 degrees warmer, you know that water is flowing from the tropical oceans, the equatorial oceans, unimpeded up over the poles. And in the cold house, something's preventing that. So ocean currents are very important. And I want to go through those. Now, here's our current configuration of continents. And as you can see, you look and you see exactly what I told you about. If you take a look at North America, look at the United States, Canada, Alaska. That's just a huge barrier to the warm waters. If you go down and look near the equator, you'll see equatorial currents. There's a north equatorial current that tends to flow from east to west. There's a south equatorial current that does the same thing. There's an equatorial countercurrent. And we've talked, of course, about how in the Pacific, those equatorial currents change direction based on El Nino and La Nina. You want to go back and look at those episodes on El Nino and La Nina. This is kind of the normal configuration where the waters in the north equatorial and south equatorial regions in the Pacific flow from the Americas out toward the Philippines. And there's a countercurrent coming the other way. Under La Nina, almost all the water's flowing from the Americas out. And as you can see from that cold water coming up off the coast of Peru. Look at that blue off the coast of Peru. That's very cold water, extremely cold. Why? Okay. Ocean currents in the southern hemisphere tend to go in giant loops in the oceans that are counterclockwise. So take a look at the South Pacific Ocean. You've got a current way down in the South Pacific that's flowing from west to east, flowing from the direction of New Zealand toward Chile. And then as it gets there, it gets bent around and it tends to go to the left because of Earth's rotation. It's very cold water because it's been way down there near Antarctica in the very southern Pacific for a long time. That water's gone all the way across the ocean at that latitude. So it's extremely cold when it gets to Peru. It moves up off the coast and then bends back, hooks to the left. It's cold and it takes that cool, the property of the cold water, and then it interacts with the air, cooling the air, and moves out across the Pacific. When it gets out to the other side of the Pacific, it bends back down. You can see that over on the other side, go way over on the other side because the Earth is a sphere, and yet we've got a two-dimensional. So you can follow that South Equatorial current way out on the right. And then when it gets near Australia, it hooks down. By then it's very warm because it's been near the equator all the way across the Pacific Ocean. It hooks down, it's very warm, and then it completes the loop. That's the South Pacific gyre. Notice there's a South Atlantic gyre with cold water coming up out of the South Atlantic off the coast of Africa. And by the time it gets to the equatorial region, it bends to the left. And then it comes down off the coast of Brazil as a warm water current, the South Atlantic gyre. You've got the South Indian Ocean gyre. Same thing, cold water down in the south part of the Indian Ocean. It's bringing that cold water. So if you lived in Australia, you know, the warm beaches, the beaches with the warm water would be on the East Coast. The beaches with the cold water would be on the West Coast. And notice the United States is like that. So in the United States, we're surrounded. We've got the Atlantic on the east. We've got the Pacific on the west. But in the northern hemisphere, the gyres are clockwise flows. Clockwise. And everybody's heard of the Gulf Stream. Well, there's nothing that special about the Gulf Stream. After all, it's just water flowing north because that's what happens in the northern hemisphere. You get equatorial water coming and it bends around to the right to go clockwise. It's very warm. It's coming out of the Caribbean. It's been in the North Equatorial region for a long time. It hooks around and it carries with it warm water. So the beaches in the Carolinas and, Florida, they're very warm water because of the Gulf Stream and because of the clockwise flow in the Northern Hemisphere and the North Atlantic gyre. The North Pacific gyre is also clockwise. You can look at it way over on the left off the coast of Japan, Kuroshio, or it says Kuroshio, off the coast of Japan. You've got a warm water current equivalent to the Gulf Stream, and it carries water into the Northern Pacific that's quite warm. If you look back way over, remember, it's just because Earth's a sphere and we've got a two-dimensional representation. The water from the North Pacific comes it pretty much strikes the western coast of the United States. A portion gets deflected and goes north and carries some of that warm water off the coast of Alaska, but the bulk of it comes down off the coast of California. If you've ever been to the beaches in California, you know the water's quite cold there. It never really warms up.
As we see the flow going around through the arrows, what about in the middle? Does the water also flow in the middle circles, or are the flow of the currents like the jet stream, where it's a thin strip?
There is not the flow in the middle of the gyre that we have where the arrows are. So let's say that you want to go deep sea fishing in the Carolinas. You can charter a boat and they'll take you out. But to go deep sea fishing, they want to get to the Gulf Stream and they have to locate the Gulf Stream. And it is like a river in the ocean. I also want to point out, before you get to the Gulf Stream, if you notice that blue, there are always countercurrents. I got to point out there are countercurrents. Look at the Labrador Current, a very cold current coming down. The Gulf Stream's going up. We know the gyre is clockwise, so it's from south to north. But that Labrador Current can sometimes hug the coast and slip down all the way past the Carolinas. You might go to the Carolina beaches, especially early in the summer, and that Labrador Current's bringing some cold water. You may find cold water. So you've got to go out to the Gulf Stream. What happens if you go out past the Gulf Stream? No, there's not, Patrick, there's not that river of water out there. When you get out there, there's quite a bit of chaos, actually, if that makes sense. There's currents, there's countercurrents out in the middle of the oceans. You know, you may find a current going north. You may find a current going southwest. It's kind of like our weather, you know, where we have prevailing westerlies, but sometimes the wind comes out of the east or south. And, you know, these countercurrents do occur. But in general, the flow in the ocean is like that. But in the middle of a gyre, you know, maybe the current is just relatively static. Maybe it's being swept toward the major current in the ocean, but it's nothing like these things. There's nothing inside the gyre that is carrying water, so much water, so fast, so powerfully as these things. So we do get a flow from Japan. The currents flow in that North Pacific gyre is from Japan toward the United States. And debris in the Pacific Ocean especially is becoming a problem. There's just as humans produce more garbage, these ocean currents carry it. And in the Northern Pacific Ocean, there are issues with garbage and debris on the surface that are being carried by these currents. And then, like you kind of indicated in the middle, sometimes some of that garbage patch, they call it, will just stay static because there's no real current to carry it.
The ocean currents sort of mirror the flow of the air.
That's
winds.
correct. That's absolutely correct. If you look at the North Equatorial Current and the South Equatorial Current, they're just like the trade winds. Trade winds are blowing from northeast to southwest, just north of the equator, and south of the equator, they're flowing from southeast to northwest and then out along the equator. and the prevailing westerlies, at our latitude look a lot like the flow of the ocean currents clockwise from west to east. So yes, they do mirror that. They do run together. And it's because of the rotation of the earth. The rotation of the earth tends to bend winds to the right in the northern hemisphere and to the left in the southern hemisphere, and it does the same to currents. So if you're a current down in the South Atlantic, you're constantly being pulled to the left. So look down at South Atlantic between Africa and South America. That flow is coming over, but it's being hooked back to the left off the coast of Africa, just like what happens to winds. In the right, currents are pulled to the right. So that's the way that works. I did want to say, though, in continuing back to El Nino and La Nina, in a typical La Nina, the north equatorial and the south equatorial currents get working, and along with the equatorial current, they push it back. And remember, we talked about how that cold water that converges from California and Peru sweeps all the way across the equatorial Pacific and cools it down and ushers in a period of cold because there's so much cold water on the surface. In El Nino, you get a high pressure system out in the Western Pacific, and it reverses all that. The equatorial countercurrent takes over and just drives very warm water back from the Philippines, New Guinea, etc. Warm water comes all the way to the Americas. And as we've seen, El Nino and La Nina can, either one of those, El Nino can warm Earth's temperature by a full degree Fahrenheit or even more in just a few months. La Nina can cool Earth's temperature, the whole temperature of the planet, by a degree or even more Fahrenheit in just a few months. That's why we have that. We don't have El Nino and La Nina in the other oceans because they don't have the distance. If you look at the equatorial Pacific, it's a long, long way from the Philippines or Malaysia to the Americas. It's not that far between the Americas and Africa in the equatorial Atlantic. Not big enough to have that kind of phenomenon. It's not big enough to have that kind of phenomenon in the Indian Ocean. Look how short those equatorial currents are in the Indian Ocean. Quite a lot different than in the Pacific. One of the things that happens, though, is that the Gulf Stream, by bringing warm water up in the direction of Europe, it gives Europe a much warmer climate than it would ordinarily have without the Gulf Stream, without that circulation. So currents tend to go clockwise in the northern hemisphere. We've gone over this, counterclockwise in the southern. We have countercurrents. I did want to talk about the south circumpolar current. If you look at the currents around Antarctica, because it is an island continent, you don't have that equivalent in the northern hemisphere. The currents are so strong there. And the jet stream, as you mentioned, does kind of like the currents. The jet stream goes pretty much over top that Antarctic circumpolar current. It isolates Antarctica, or much of it, from the rest of the world and keeps it cold. And that's why the fastest warming place on the planet is the Arctic. But the Antarctic is not warming at all. People say, well, if the Antarctic's not warming, maybe global warming is false. No, Antarctica is being protected. It's being isolated by these very strong air currents and ocean currents. And that's one thing I mentioned before and wanted to go over that. It's cut off from the global flow. And yes, there's your answer accompanying the jet stream. If you look at the very bottom, Antarctica is essentially cut off from the global flow by this strong current and the accompanying jet stream. And that's the slide we finished off with last time that shows that. If you look in the Southern Ocean, at the flows around Antarctica, and again, if you look at the overall outer flow, the Antarctic Circumpolar Current, yes, that's underneath Australia, south of Australia. It blows over off the coast of South America. It flows from south of Australia all the way underneath the Pacific Ocean in what is now scientists are calling the Southern Ocean, between South America and Antarctica. It continues to blow south of Southern Africa and comes on around in a giant circle. Okay, well, that doesn't quite happen in the Northern Hemisphere, because in the Northern Hemisphere, even though the North Pole, like the South Pole, they're both cut off a little bit from warm equatorial waters.
We're talking with Dr. Thomas Blaine. He's an associate professor with the Ohio State University Extension Program. Listed below in the description is a lot of information that Tom wishes to share. Tom, thank you. This has been a very informative video. I'm Patrick Dangle. Thank you for viewing.